Many of you know, midterm 2 is coming up, so I thought I'd make a quick review for you guys. And the slides for this PowerPoint are also posted on Canvas with all the solutions as well, if you'd like to look into that. So we're just going to start off with a simple cache question. And before we do each of these questions, I'll also give you a quick moment to pause in case you want to try it before I go over it. So for the first question, suppose we have a physically indexed, physically tagged cache, and all the physical addresses are 12 bits. So the cache is direct mapped and has 4 sets, and the block size is 16 bytes. So you just find the following statistics: the cache size, the index size, and the tag size, and the number of bytes and bits, respectively. Okay, so I'm assuming you've paused the video now and done the problem. So the first thing you want to do is you want to find the cache size. So the way to do this is to first check it has 4 sets and each block size is 16 bytes. Since it's direct mapped, we know it therefore has 4 entries, and therefore it has 4 blocks of 16 bytes. 4 times 16 is 64. So we get 64 bytes for the cache size. Now for the index size, this is entirely based on the sets, no matter what type of cache it is. So here the sets are 4, 2 squared is 4, so we know that the index size is 2. And another way to do this is just take the log base 2 of the number of sets to get your answer. So for example, if it has 4 sets, log base 2 of 4 is 2. If it has 8 sets, log base 2 of 8 is 3, etc. Now lastly, for the tag size is what's left over from the index and the offset. So you find the index and the offset and then take the address size and subtract those two to get the tag size. So we already found the index size is 2 bits. But we need to find what the offset is. So the offset is always based on the block size, which here is 16 bytes. So again, we can do the log base 2 method. So log base 2 of 16 is 4, or also 2 raised to the power of 4 is 16. So therefore we know our offset is 4 bits. So our index is 2, offset is 4, our total address is 12, so it's just 12 minus 4 minus 2, which gives us a total of 6 bits for the tag size. Okay, so now I'll move on to the next question. So this one's a little longer, but assume the following cache configuration. The cache size is 4 kilobytes. The cache line size is 64 bytes, and each address is 32 bits. So for the following sequence of memory accesses, just find the index and tag for the specific cache configurations. And I know the memory addresses in the bottom left there aren't the full 32 bits. You can assume they're 0 extended. It's just I was having trouble fitting everything onto the slide. Okay, so again, hopefully you've paused the video and done this so we can get started on solving it. So the first thing we should look at is the direct mapped. So for direct map, it's all just sets, as you know. So we need to find the number of sets first. So since there's no associativity, we can do this pretty straightforward. 4 kilobytes, which is 2 raised to the power of 12, is the cache size. So that's 4096 divided by 64, because the cache line size is 64, which means we have a total of 64 sets. So now that we know the number of sets, it's quite easy it's quite easy to find the number of index bits. So log base 2 of 64 is 6, or 2 to the 6th is 64, which gives us the direct mapped index size of 6 bits. The offset for all of these is always based on the block size, or in this case, it's called the line size. They're the same thing in this instance. Again, 64 bytes, we index into that. It's just 2 to the 6th is 64 again. So we know our offset is 6 bits and our index is 6 bits for direct mapped. So we take the offset is the least significant 6 bits, the index is the 6 bits after that, and then the tag bits are the most significant 20 bits. Since 6 bits, that's 12. Address size is 32 bits. 32 minus 12 is 20. Again, you can just assume this tag is 0 extended because yeah, that's a lot of zeros to type in. Next up, for the 4-way set associative cache, now we have a bit of associativity as well. So the cache size is still the same and everything, and the cache line size is still the same. So since the cache line size is still the same, we still know that it has 6 offset bits. So now we just need to find the number of index bits. So for this, the cache size is again 4 kilobyte, which is 4 raised to the power, or 2 raised to the power of 12. So 4096. We have 64 entries, just like the last, or we have 4096 divided by the 64 bytes, just as last time. So now we have 64 items in our cache. We know this is 4-way set associative though. So we know each set will have 4 ways attached to it. So we can divide this 64 by 4 and find that we have 16 total sets. So then we take log base 2 of 16, which is 4. Same thing, 2 to the 4th is 16, which gives us 4 index bits. So we have 6 offset bits, yes, from the cache line size, 4 index bits, which we just found, which means the remaining 22 bits are the tag bits. And again, that's just 0 extended, but wasn't going to write all that. Now, for fully associative caches, there is no indexing, right? So we don't really need to worry about the index bits at all. It's just, they just don't exist, or 0. There are 0 index bits in this case. Additionally, for the tag bits, you still need to consider the offset. So 64 by cache line size will keep the 6-bit offset. So everything after that will just be the tag bit. So the remaining 26 bits will be the tag bits, and there will be no index bits. So the same thing for each one respectively can be done below, right? It's the same stats, the same number of index and tag and offset bits. It's just an exercise in extracting these values from the actual address. So I'm not going to go through it all again, but you can see here it's the exact same statistics. So the direct mapped will still have 6 index bits, same amount of tag bits, etc. Okay, now for the first virtual memory question we have. So remember that the virtual address is interpreted as the virtual page number followed by the offset, and a page table holds the mapping of virtual to physical pages. So let's suppose that virtual and physical addresses in the system are 16 bits, page sizes are 64 bytes, and each page table entry is 2 bytes wide. So what in this instance would be the size of the page table in bytes or kilobytes or whatever you want to do it? Okay, so I'm assuming you've paused it, done the question on your own. So to begin with, we need to find the number of offset bits. So in this case, the page sizes are 64 bytes. So the offset is just log base 2 of 64, which is 6. Or again, 2 to the 6th is 64. So you have 6 offset bits, which means the page table, the virtual page number we're using to index the page table is the remaining 10 bits of the address, right? Because the addresses are 16 bits in this instance. Therefore, we know that since you have 10 bits to index, we know there are 2 to the 10th entries in the table. And 2 to the 10th is 1024, so we know there are 1024 entries, and each of these entries are 2 bytes wide. So we can do 1024 times 2 bytes, and that gives us 2 kilobytes, as shown below. Okay, now for another virtual memory question following the TLB. So consider a 4 gigabyte virtual address space with 32 kilobyte pages. Assume the following TLB state on the right. What physical address will the reference 0x69540C88 generate? Okay, assuming you've completed the question, we'll move on to the solution. So the first thing you know is that the page sizes are 32 kilobytes. So we can use this to find the offset by just doing the log base 2 of 32K, which is 15 bits. So now we can take the least significant 15 bits off our virtual address to be used as the offset. And remember, the page offset doesn't change from the virtual address to physical address in this instance. So we just take that and we're going to append it on to the end of our physical page number when we find it. So now we know that the remaining bits are the VPN, which you can see below, below where the calculations for the page offset are. So you go to this VPN turns out to be 0x0D2A8, which you can see is the second entry in our TLB here. The virtual page numbers match, and it is valid. So it's important to check it's valid, of course. After that, you can just get the physical page number from that, which is 0x1234. So you just take 0x1234 and you append the page offset we found earlier to it, and that gives us the final physical address of 0x091A0C88. Using this same system with the same 4 gigabyte virtual address space with 32 kilobyte pages, if each page table entry had 32 bits, how large in bytes is the page table to track the status of all virtual pages in this process? Okay, so assuming you've paused and finished the problem, the first thing we want to do is we want to take we want to find the size of each address. So the 4 gigabyte virtual address space corresponds to 32-bit addresses. So using this fact, we take the 32 kilobyte pages to find the page offset, which again is 15 bits, just like we found previously, which means the remaining bits are used for the virtual page number. So 32 minus 15 is 17 bits. So we have a page offset of 15 bits, and we should have a 17-bit virtual page number. Since you use the virtual page number to index into the page table, we know there are 2 to the 17th pages in total. So this is 131,072 total pages in the system. Each of these has a 32-bit page table entry in the page table, right? Because it says each page table entry contains 32 bits. Therefore, this is 4 bytes. 32 bits is 4 bytes. So the page table size is just 2 to the 17th times 4 bytes, which equates to 512 kilobytes. Okay, so now for our last question. Just a simple AMAT question for caching. So find the average memory access time for a single layer cache with the following characteristics. A hit time of 1 cycle, miss rate of 25%, and a miss penalty of 70 cycles. Okay, so I'm assuming you've done this problem real quickly. So the first thing you do is you use the AMAT equation, which for just a single layer cache would be the hit time plus the miss rate times the miss penalty. And if you have multi-layer caches, you can append this miss penalty, or you can kind of cascade the equation as shown in the lecture slides. So in this instance, all you have to do is take the hit time of 1 and add it to the miss rate times the miss penalty, which would be 0.25 times 70. And that gives a total of 18.5 cycles for the AMAT. Okay, so that was all the questions I have for you today. Thank you for watching and good luck on the exam.